So we've talked a little bit about calorimetry already, and we talked about like what we call just a normal calorimeter. It's a coffee cup usually, or insulated container like a thermos, and you do a chemical reaction in it, and you measure temperature changes. So there's this unusual device. I think it's kind of unusual, but it has a very important purpose. It's called a bomb calorimeter. This is actually how they measure the energy content of your food. And what the bomb calorimeter doesn't allow to happen is it doesn't allow the volume to change. And so delta V is 0, which means W is also 0. I got to change these bullets to not be negative signs. So delta E, the change in internal energy that you see for a reaction, will be directly related to the heat that you measure. So this is why this is a useful measurement for something like food calorie content, because we just want to know how much energy is in the food, and so we'll use a bomb calorimeter. So what it looks like is like this. There's a thermometer, right? An ignition wire, which you might expect in a bomb, right? This is the bomb, and I've always just assumed that it's called a bomb because if the reaction goes awry, this is actually a bomb. I mean, it'll blow up. And then we put water in it, and then what we do is we run this paddle around to stir the water and uniformly distribute the heat in the calorimeter. So what happens is you measure the temperature in the water, okay? You fire off this reaction with a substance of known energy, and then we measure the temperature change. And what we get is a heat capacity, a C, not a specific heat. It's often called a heat capacity, because what you're not taking into account is mass. You're just saying for this whole object, right, how much energy does it take to change its temperature? So this is how you set up a bomb calorimeter. Let's look at an example problem for the calibration of a bomb calorimeter. Okay, so a bomb calorimeter needs to be calibrated first, and we're going to be finding out the calorimeter's heat capacity, or also known as the calorimeter constant. And the equation that it goes into is like the MCAT equation, except for it's just Q is equal to C times delta T. Because when you're doing this experiment, you're not weighing the calorimeter. That doesn't really factor into any of this. We just we're going to put a sample in it just to calibrate it. So let me read the problem to you. It says you have a 1.08 gram naphthalene sample, right? Grams of this, and it's ignited in a bomb calorimeter, and it produces a 5.92 degree temperature change. What is the calorimeter's heat capacity? And then it says naphthalene's heat of combustion is negative 5,153.5 kilojoules per mole. Okay, so you stick in a sample of naphthalene, then there you have 1.108 grams, right? And this is going to be ignited, so it's going to produce heat. So now we have a Q for my calorimeter, right? And I know that the Q for the combustion are going to be the same, except what? That there's a negative sign in here. So the heat gained by the calorimeter is the opposite of the heat lost by the combustion of the naphthalene, okay? And so what I'm going to do to solve this problem, I know that Qcal is equal to C delta T. I'll need to find out how much energy is lost by the naphthalene in the combustion. So I'm given the heat of combustion, which is in terms of kilojoules per mole, and I'm given grams of naphthalene. This is C10H8. And so the problem to solve for the energy is simply grams to moles. And once you have the moles, you can calculate the kilojoules of energy for that reaction. So 1.108 grams of naphthalene, it's 128 0.17352. I don't know where I got all those digits from, but grams per mole. I probably used a really good periodic table of C10H8, and then that produces negative, right, 5,153.5 kilojoules per mole. So you do this calculation. This will be your Q, right, for the naphthalene, the C10H8. I'll just call it CH for now. And that comes out to be negative 44.549 kilojoules. So Q-cal will be the opposite of that value, and so it will be 44.549 kilojoules, and that's going to be equal to C delta T. So to calculate C for this calorimeter, I just need to take 44.549 kilojoules and divide it by the change in temperature, which is 5.92 degrees Celsius. And that will give me a calorimeter constant or heat capacity of, 7.525 3 sig figs kilojoules per degree Celsius. Okay, so that's a heat capacity calculation for calorimeter. And then once you've done this with the Bomb Calorimeter, you've calibrated it and you know how much the temperature change is per kilojoule, right, or the kilojoules per temperature change unit. You can use that to measure heat that's produced by other substances and calculate heats of combustions or energies in other kinds of substances. So now we're going to use that heat capacity that we just calculated, and it says I have 1.315 grams of thymol. There's the molecular formula and the molar mass, right? Is ignited in the same calorimeter, that's the one we just did, and a 6.74 degrees Celsius increase is observed. Calculate the heat of combustion for this substance, the heat, the energy, or enthalpy, or heat, per mole of thymol. Okay, so I know Q, right, is equal to C delta T, and I can calculate the heat for this reaction because from the previous problem, we figured it was 7.525 kilojoules per degree Celsius. So 7.525 kilojoules per degree Celsius, and then we multiply by the temperature increase, 6.74 degrees Celsius. This will cancel, and I will end up with 50.72 kilojoules of energy released. Now, the enthalpy, that's the heat per mole of thymol, sorry, too many moles going on. All I need to do to get that value is divide Q by the number of moles. So now I convert 1.315 grams of thymol into moles. So this is 150.22056. Man, I got some crazy molar masses back in the day. Probably don't need that many sig figs of C10H4O, right? And then that's going to come out to be 0.00875338 4 sig figs, so there, right, on the 3 moles of the substance thymol, C10H4O. And now I can calculate enthalpy. I have to do one other thing, though. This is Q for the calorimeter. right? And so the Q for the combustion is equal to negative Q of the calorimeter using conservation of energy, right? And then what we find is that Q, or let's just call it the enthalpy, is going to be 50.72 kilojoules divided by 0.008753 moles. And 4 sig figs in my calculation, I think. Let me go back and check something. Actually, this is 3 sig figs here. That's what I was thinking. So there's 3 in this number. So the answer comes out to be 5,790 kilojoules per mole, like that. Okay.